So I'll give you some insight to some sort of, and sometimes kind of old fast imaging approaches, but things we still very much use today. And then we'll have a fast imaging lecture that focuses on what's called parallel imaging and sensing. I think that's next Tuesday. No, 2 Tuesdays from now. At any rate, so Peng Hu will talk about that topic, so you'll get even more sort of fast imaging information as well. This is the learning objectives, just reviewing from the last lecture. And what we finished with in the last lecture was this expression. And this is a really, this is an important one. You're likely to see something related to this on the final exam, because it's really important for understanding the behavior of signal to noise in the MR experiment. And in fact, this will be useful in your lab, which is next Wednesday. And the very end of this lecture is about, I don't know, 10 or 15 slides, where we're going to go through what I call protocol optimization. So you start off having designed some protocol to obtain some images, but the image quality is no good. What can we do to sort of change image quality and finally get to an acceptable protocol? And in some ways, this will be very similar to what you need to do in your lab on Wednesday. So it's sort of kind of a class exercise for that. You'll see it in the lab. We'll go from there. The simplest expression that we saw for signal to noise is the one that's on top, and then it's sort of explained a little bit further on the bottom. So on the top, it just says that the signal to noise is proportional to two things. It's proportional to our voxel volume. And our voxel volume, we think of pixels, but our pixels have thickness, so we call it voxel. And our voxel volume is pretty easy to spell out. In fact, it's everything in front of the square root that's shown on the bottom here, right? So it's our field of view in the x direction divided by the number of encoding points. I wrote nkx here, but that's nkx is also equivalent to the number of image points, right, if we do a one-to-one linear reconstruction. And so this is basically the voxel width. This is something like the voxel height, right? And then we have h for the slice thickness. So this would be the 3 linear dimensions of your voxel size. And it should make sense to you, right? The larger your voxel, the more signal you have. So hopefully we're good there. What's inside the square root is a little bit less obvious, but we'll pick through it a little bit. Part of what we saw was that the signal to noise is proportional to the square root of scan time. And so that sort of told us that we could improve our signal to noise by scanning longer, right? Longer time is better signal to noise. But unfortunately, there's this sort of square root penalty. And so it's pretty obvious for you guys, right? If I increase my scan time by a factor of 4, I can only improve my signal to noise by a factor of 2. So it's kind of a slow gain in signal to noise, or even an expensive gain in signal to noise. Now, the things that govern our scan time, some are obvious and some are a little bit less obvious. So you described this before, but we'll do it one more time. Obviously, the number of points that we're encoding, right? The more points I'm encoding, the more imaging information, or the longer it takes me to obtain that imaging information. So you can rework this, right? I'm trying to be explicit about voxel volume and things related to scan time, but obviously there's nkx is showing in 2 places. You can change that if you want to. So inside the square root, the longer our readout, the more imaging time. The more phase encoding steps, the longer our imaging time. If we choose to do averaging, repeat the scan more than once, the more imaging time. So those all extend the time we spend imaging. Bandwidth, this is what we call the readout bandwidth, or the receiver bandwidth. Again, different from the radio frequency bandwidth, or the transmit bandwidth. The receiver bandwidth on the bottom here is really related to how fast we move across K-space. If we use a large gradient, we can move across K-space quickly. If our bandwidth is high, then this time is going, this bandwidth is high, and this time is going down, and our signal to noise is going down. So high bandwidth decreases signal to noise. Alternately, we can lower our bandwidth, right? We could move across K-space slowly. That's equivalent to having low bandwidth. If we have low bandwidth, then we're extending our imaging time and our signal to noise. So everything's a trade-off. What other consequence does changing bandwidth have on our images? We talked about how it's related to signal to noise. What's another image feature that it's related to? The transmit RF band, that is. So the other bandwidth, the RF pulse bandwidth. But for the receiver bandwidth, there was something else it was related to. What's the difference between fat and water? What's an important difference about fat and water at all? In what way are they? What's one way in which they're different? Chemical shift. So what does that mean? So fat has a chemical shift relative to water. What does that actually mean if it's shifted?
It's alarm frequency is different
Yeah.
because of the molecules.
Yeah. So it's all hydrogen still, right? Like there's a bunch of CH groups that build up fat, but its chemical environment is different than the environment of water itself, which is close to water, but not, say, carbon groups. And so, so fat is chemically, so to speak, chemically shifted from water, and it has a slightly different resonance frequency for the same V0. It has the same gyromagnetic ratio. It's still hydrogen in water, hydrogen in fats, but the chemical environment shields the nucleus, and that means that the very, 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 very local field can be slightly different. Okay. So fat and water have different resonance frequencies. When we turn on, say, a readout gradient, we're creating a range of frequencies across that specific direction, right? So if we're reading out in the x direction, we have a range of frequencies in the x direction. Fat and water will also have a range of frequencies, but because of this chemical shift, fat will appear as if it's coming from a different position, because it will resonate similar to a different position. So we get chemical shift artifacts. So depending on the bandwidth is related to the strength of your gradient. The strength of your gradient governs the range of frequencies across the object. And so if we have a large range of frequencies across the object, because we have a high bandwidth, we'll actually have a small chemical shift artifact, because that shift will be, in frequency terms, small compared to the total bandwidth. So high bandwidth is bad in that it will decrease our time, our imaging time, and decrease our signal to noise, but high bandwidth is good because it will mitigate or reduce chemical shift artifacts. And then you can work through the opposite example of low bandwidth being increased signal to noise, but also increased chemical shift artifacts. So we went through this first example at the very end of class last time, which was just about having the slice thickness. So if our voxel volume or our slice thickness goes down by a factor of 2, but we want to get our SNR back, then we have to maintain our signal to noise, we have to scan by a factor, scan 4 times longer, right? So it's a steep penalty to pay for thinner slices. Right? You could work through a different example where we say, okay, well maybe your protocol is such that you're okay with doubling your slice thickness, so now your thickness here has gone up by a factor of 2. That means in principle you could scan in a quarter of the time, right? You don't have to spend as much time scanning, and you can get the same, say, signal to noise. The trick will be in how can you adjust these parameters such that you can actually reduce your scan time by a factor of 4. For most of our protocols, for example, the number of k points and number of kx points and number of ky points, we don't necessarily have a lot of flexibility that we've chosen those for the purposes of resolution. We'll talk today about some ways where we can do some undersampling, say in the ky direction. And in fact, there's additional methods we'll learn about in probably the Clues lecture on parallel imaging. And of course, you can decrease the number of averages if it was something other than 1. Most protocols, it's going to be 1, just because scan time is so precious, but not always the case. And then here's sort of the third example. So in general, we said this a lot of times, our FOV, our field of view is fixed, right? We have an object that we're trying to image, and we sort of make the field of view small enough to adjust and match that object. And so if you want your resolution to go up in general, you have to increase the number of k encoding points in x or y direction. Interestingly, that's going to result in increased scan time, right? So you're going to decrease your resolution here, so your voxel volume is getting smaller. But as the n encoding point shows up in here too, you're also getting some boost from having scanned for longer. Overall, however, that will still give you a net reduction. So you could work through the specifics of what that reduction is. It's quite okay, so I think that's most of what I was going to sort of review for the last lecture, just because this is an important equation in general, and you'll use it in the lab on Wednesday. Good. this topic I touched on, but I don't know why I pulled the slide down, so I want to go through this again for you guys. When we acquire our k-space data, you basically have a matrix of k points, and those points just fill the matrix, right? The matrix doesn't really have any sort of physical dimensions to it, it's just numbers entered into an array. One thing that we can do, or at least the definition of zero padding, is appending zeros to our k-space data before we do the Fourier transform. And you typically will append those symmetrically about k-space. So you have a block of k-space, and in the matrix that you have in MATLAB, for example, you can append zeros above k-space and maybe below k-space in a symmetric way. And that's actually equivalent to, if you think about it, right? So if I add even if it's zeros, if I add zeros above my k-space and below my k-space, what kinds of spatial frequencies have I added to my k data, even if they're zeros? So high or low? High, right? So in principle, you added some high spatial frequencies, but it's just a bunch of zeros, right? Well, that still has an effect when you take the 2D Fourier transform of resulting in an image matrix that has the dimensionality of your k-space matrix, even if it was zeros. And we call this sync interpolation or zero-padded interpolation. There's a couple different reasons why you might want to do that. The matrix that you use for acquisition may not actually be 2 to the n, and the fastest Fourier transform algorithms that we have use what's called the radix 2 fast Fourier transform if your matrix is 2 to the n. And so if we have an acquisition that's 256 by 192, 192 is not 2 to the n, we can zero pad it to 256 by 256, and then the Fourier transform will be a little bit faster. There's a couple of effects. One is that it will increase the digital resolution, right? Your digital camera does this. You have an optical zoom of 3x or something like that, and then you'll have a digital zoom that's 2x or 100 million x, right? It's arbitrary. So it's a way to arbitrarily increase the resolution, but it's not really an increase in resolution because after all, you didn't add information, you just added zeros. And I'll show you an example of this, but it's also another way of reconstructing with the correct aspect ratio. And that's not a completely obvious thing, but I think the examples are cool. So let's begin by thinking about some low resolution data. We did some acquisition of 64 by 64. If we take a 2D FT, then we get an image. What's the dimensions of our image? If this was 64 by 64, the matrix resolution is 64 by 64. We can obviously blow that up, right? We can just stretch it, but in doing so, I'm going to have these kind of blocky pixels, right? And so if you use Osirix or imaging tools, you actually have an option. You can zoom in on the image, and it'll keep the pixel resolution sort of accurate and make these kind of big blocky pixels. I prefer that because it actually tells me like what my data looks like, right? Another option is to turn on, I forget what they call it in Osirix, but other imaging viewers have the same. What's that? There's an interpolate kernel, yeah. So you can flip that on, and then this image will look smoother. I don't necessarily prefer that. Now, something that we haven't talked a lot about is the possibility of having so-called asymmetric resolution, right? We pick our field of view, matches our object. The next thing is to pick the encoding dimensionality, right? Number of readout points, number of phase encoding points. Those don't have to be the same. In fact, our field of view doesn't have to be square, and our matrix doesn't have to be square. Both of those could be rectangular. And so in this case, let's say I acquired a K matrix that was 32 by 64. What's different between these two acquisitions? What am I missing in this 32 by 64 acquisition? What kinds of spatial frequencies are missing? High, right? So I didn't get this higher spatial frequency information. My delta K must be the same, right? My delta K is the same because my field of view is the same. My soul is trying to encompass the same object. If, however, I just take a 2D Fourier transform with this rectangular array, I'm just going to get another rectangular array, right? It doesn't magically become the right aspect ratio. So the pixels are square, but in fact they shouldn't be, right? In MR, we can have rectangular pixels because we can choose the dimensions of our pixel through our field of view, but also the number of encoding points. And the number of encoding points in readout and phase are independent of that. And so what you really want, it's not this squished and kind of funny-looking image where the pixels are square, but you didn't acquire square pixels. What you really want is a stretched-out version, right? Like this is true to form. This has the geometric fidelity or accuracy, if you will, of the actual underlying object. So the question is, how do you do that stretching? Well, one is just to use zero padding. And so if we take the same K data, add zeros on the other side, above and below, take the 2D Fourier transform, then we can reconstruct an object that has the right dimensionality to it, if you will. It has square pixels that, because our imaging displays have square pixels, it'll give us back the right aspect ratio for the underlying object. So that's one of the probably most common reasons to use zero padding, is to restore the aspect ratio of the acquisition. Okay. So that was a topic I didn't quite get into, or didn't get into as much as I wanted to previously. It's going to come up again. That's why I'm interested. What we're going to talk about now is a little bit qualitative. It's just the way everything that we've been considering so far. I've been showing you lots of different movies, and some of those have motion in them, but we haven't really talked about the effects of motion on imaging. Rather, we've just sort of assumed we have stationary objects and that motion isn't really a factor. This is going to be a qualitative insight to sort of the effects of motion on MR imaging, because it leads to some interesting artifacts. When Holden comes to speak end of next week from today, he'll talk more about motion and actually measuring motion. MR is a really wonderful measurement instrument, although it still needs some work there to be an excellent motion estimation instrument. So motion in general is responsible for corruption in the spatial localization and the phase encoding in particular, and that can result in blurring and or ghosting artifacts. And we'll get into this, but the main reason it affects the phase encoding direction rather than the frequency encoding direction is that when we're reading out lines of K-space, that happens quick, right? The plateau during which we actually acquire data is only a couple milliseconds. And motion during that interval has, motions, typically the motions we care about are not fast enough or high enough to really be relevant in a 2 millisecond time scale or a 1 millisecond time scale. Phase encoding happens slow, right? Phase encoding happens every TR, and that could be either several milliseconds or even hundreds or thousands of milliseconds. And now the object could be in different places with every phase encode, and that, as you'll see, can lead to phase encoding artifacts. Lots of different possible forms of motion when it comes to imaging, say human subjects in particular, right? Patients like to wiggle around, prefer to breathe, it's hard to get their hearts to stop, and then there's all kinds of things happening in there as well. So lots of different forms of patient motion. Some of these are a little bit easier to deal with than others, right? So patient motion, you can certainly deal with it, so to speak, just through coaching the patient and saying, look, this is really important, and when you hear the scanner buzzing and clicking, it'd be great if you could hold as still as you can. Right? So that can kind of be managed that way. But it's a very typically aperiodic form of motion, right? If they move, if they cough, if they sneeze, if they scratch, like those are things that you don't know when that's going to happen, right? And so that can make it tricky. You can sort of coach it, but when it happens, it's not sort of exactly the way. Respiration is quite periodic, right? And there are lots of ways, lots of MR-based methods, lots of instrumentation-based methods for monitoring respiratory motion and trying to either synchronize the imaging instrument to a state or phase of respiration, that's probably the main way. So somehow track the respiratory motion and synchronize imaging to particular states. And cardiac motion, or otherwise vascular sort of pulsatility and so forth, can also be monitored, and imaging can be synchronized to it. Again, Holden will talk about this a little bit more, but what do you think is the easiest way to synchronize imaging to cardiac motion? How would you think about doing that? ECG, right? So we can put ECG leads on your test, we can ECG, and then we can tell the scanner to do certain things right when the ECG comes through or with some time delay. So there's an easy way of synchronizing. Turns out that's not a completely perfect system. It works quite well, but it's not entirely foolproof. But we won't get into that too much. And then obviously sort of peristalsis, bowel gas movement, and so forth. That's a tougher problem to deal with, right? Difficult to monitor, difficult to know when it's happening, difficult to control, and yet can lead to imaging artifacts. Right. Well, okay. So this kind of, hopefully it's obvious at this point, but obviously we're recording K-space signals, not images directly, right? And so there's this possible discordance between what data we're acquiring and what's happening in the object itself. And that'll be more obvious in some examples. So this is a really a couple simple examples that actually Keone put together a couple years ago. So just imagine this maybe is head motion, right? You've got a phantom, and somehow this patient is managing to move their head sort of, relatively far during the acquisition, right? And this, again, there's different examples of possible motion. Now, the trick is that when we fill k-space, typically the k-space trajectory that we use, this is Cartesian k data, right? It's just the grid of k points. And oftentimes we're going to acquire that data from the beginning to the end. Sorry, I don't know why that's supposed to be. So we're acquiring k-space data from the top through to the bottom. But as we're acquiring our k data, our object is actually in slightly different places, right? So now there's this kind of correspondence problem. And when you go to look at what happens to the images, if this is the acquired k-space while this object was moving as it was shown, then you end up getting an MR image that kind of looks like the object that you had before, but it has these sort of ghosting artifacts. Don't mistake this for Gibbs ringing, right? There might be some Gibbs ringing in here, but I think it was filtered on recon, so there shouldn't be too much. This is more of an artifact that sort of occurs well outside of the object, right? Gibbs ringing is kind of bouncing around mostly inside the object. Respiratory artifacts tend to be more apparent kind of throughout the field of view and certainly outside the object itself. And it sort of stands to reason, but maybe I didn't say it explicitly, but it's going to be a phase encode artifact, right? We try to make the distinction when we can between phase encode artifacts and frequency encoding artifacts. Somewhat remarkably, and the Lauterbur book goes into this in more detail, but if there's motion left-right, because during frequency encoding, it has a far less, much smaller impact on the resultant image quality as compared to moving around in the phase encode direction during acquisition. Right, and so this is, I'm going to turn this down at least for a little bit. And so this is just making the point again that with the object in this position within the field of view, maybe this is the k-space that I acquired, and the 2D FT of that k-space is kind of this silhouette. It was one of the artifactual sort of features that you saw in the combined image. And then just linearly stepping through, now the object is moved down, we actually acquire a different set of lines of k-space, and the 2D FT of that is this other sort of ring. And so this is why that object that's sort of representative looks a little bit like the object. It's kind of high spatial frequency stuff because we're in the higher spatial frequency range, and it gives you a pattern that's some part of the underlying object, but in a location that's more well represented by the object's current location. And then we can just step through the different points in k-space. We get the middle of k-space. Here now you do actually see some Gibbs ringing in addition to, well, there's not much of a motion artifact there, just the Gibbs ringing. And we can step through the other blocks. And the point is that what that final composite image looks like is basically the superposition of these different sub-images. Right? It's all a linear transformation through the Fourier transform. We're basically adding those features together to give us that final artifact image. So that when we take the 2D Fourier transform of all of those funny-looking images, all of these blocks of k-space to get those sub-images, but rather combine them, then you're going to get this artifact image in the end. And so stepping through that, you can actually see that, in fact, there was some Gibbs ringing for that middle part of k-space, and then there's all this other sort of motion artifact nonsense that's outside of the direction. So there's a few things that we can learn from this. One, we get this appreciation of sort of why motion during phase encoding is problematic. The other thing you can do is you could look at an image like this. I don't know if you'll need this on Wednesday, but when you're in lab on Wednesday, it can help you identify what's the phase and frequency encoding directions. Right? So if you were just given an image like this, you'd have a pretty good guess that frequency encoding is left-right and phase encoding is up-down. And so it's one way of getting some insight to the acquisition that was acquired. And then you can start thinking backwards about, well, could the patient possibly be moving this way? And sometimes patient motion, like away from the table, sort of makes sense, right? They're lying on a table and they move their head up and down, or they're breathing, something like this. So that kind of makes sense, whereas you don't expect sort of as much like left-right motion if they're lying on a table. So it just helps give you some insight to the overall imaging problem when you can look at artifacts and think about why they're there. So this is some acquired images. In the middle, when we're doing abdominal imaging, so this is the chest wall, this is the back, This is liver. When you're acquiring images like this, and we'll see some examples of this at the very end, you typically do this during a breath hold, right? If you're doing thoracic imaging or abdominal imaging, it's relatively straightforward to ask patients to hold their breath for 10 seconds, even 20 seconds. If we don't do that, then the image quality can look much worse, right? So during that 1 minute acquisition, or however long it takes to run your protocol, if they're breathing the entire time, the image quality can be terrible. It's perhaps a little bit better if we can change the phase and frequency encoding directions, right? So on the scanner, we can choose if we want to phase encode left-right, phase encode anterior-posterior, or something else. So what's the phase encode direction for this acquisition of red? Yeah, right-left, right? So the motion artifact, it might not be really apparent that it's in the left-right direction, but it's definitely not in the AP direction. There's really no artifact at the bottom and no artifact at the top. So you can choose that on the scanner, the direction of frequency encoding. And then it's probably obvious at this point, but what's the direction of phase encoding for this image? Yeah, we call AP or anterior posterior. So clearly the artifact is kind of spraying out more up down. Admittedly, it'd be a little tough to say that there's no artifact in the left-right direction, but you sort of look for these kind of concentric patterns, right? Similar to that case-based example we were looking at, patterns that look a little bit like the underlying object, but kind of emanating out in a particular direction. Okay, so what are our options here? I mean, there's a few, right? So asking patients to hold their breath. We can do so-called respiratory gating. We can actually put a bellows, or just basically a rubber band, pneumatic rubber band around their belly, and monitor respiratory motion that way. There's all kinds of ways to sort of ask patients to reduce overall body movements through coaching. Physical restraint sounds kind of terrible, right? But there's blankets and there's padding and there's things that you can do to make sure they're comfortable and less likely to sort of move around. And then in the most extreme cases, patients that really just can't, it's infrequent to be sedated for this reason, but some patients really have to have an MR exam for diagnostic purposes. They're going through say, particular therapy, and they need to know exactly what's going on. Or for young children, for example, then sedation or even general anesthesia could be an option. The exam was so important to them. Disadvantages, of course, is that anytime there's respiratory motion, your best option is to image as fast as you can. So we'll talk about some fast imaging options today. If I can get my image in, a few hundred milliseconds, maybe motion doesn't matter to me very much. But if it takes me, many seconds or minutes, then these forms of motion are more of a problem. We can always, it's obviously a disadvantage in increasing the scan time. It's going to restrict your available TRs, and then patient acceptance and discomfort. It's always something we have to manage. Okay, so let's look at a different kind of artifact. So rather than sort of a bulk motion artifact, which you can think of as patient motion, here's another problem. Start it over again here. So here we have a stationary object, and then you have this thing in the middle that's blinking, right? Why is it blinking? Well, it's blinking at least to begin with according to some pseudo-sinusoidal pattern. So there's some signal in the middle of the body that's high and then low, and then high and then low, and high and then low. The reason you'll see things like that in MR is usually related to blood vessels, right? So you have some pulsatility because of cardiac periodic motion, right? The heart beats, and then something happens in the vessels at a slightly delayed time. The reason it ends up looking so bright, we haven't talked about this effect, it's called an inflow effect. You have to imagine that in a slice, let's think of this as a slice right through my chest, right, an axial slice. There's blood that's flowing in and out of this slice constantly, right? The blood that flows into the slice is new blood, and it has its full magnetization available, right? It hasn't been touched by an RF pulse. And so then it begins to see some RF pulses, and consequently it's quite bright because it's only seen a couple of RF pulses. All of the other tissues in that slice, the chest wall, the muscles, the organs, they've seen dozens, hundreds of RF pulses. And so they actually end up with a slightly attenuated signal because of what we call steady state effects. So new spins or inflowing spins tend to be quite bright. Stationary spins within a slice, they have a steady state signal that ends up being lower than the total available amount of magnetization. And so now we have an interesting situation. We have pulsatile blood, right? It's flowing in and out at slightly different velocities, and then you have stationary tissues. And so what happens in our images? as we're acquiring these images, this thing is beating, right? It's brighter, darker, brighter, darker. So depending on exactly what lines of K-space we're acquiring, the stationary stuff all looks the same, but this pulsatile artifact is brighter and darker at different parts of K-space, right? And so when we take the 2D-FT of this acquired K-space when we have this pulsatile artifact, what we end up seeing is something centrally that looks mostly like the thing we care about, mostly bright and like the vessel itself. But then also, again, in the phasing code direction, you'll see these sort of replicants, these sort of periodic replicants of the underlying vessel itself. And this can happen for many vessels, so it just depends on what the specific anatomy is. So let's pull this one apart and see what's happening. So we really have two things, right? We have a static object that's underlying everything, and then we have this moving object, if you will, that's overlaid with that. We can look at the 2D-FT of both of these, and the 2D-FT of this is really unusual because as we're acquiring K-space, sometimes there's an object, sometimes there's not an object, and so you get this periodic sort of banding artifact even in your K-space data itself. And when we take the 2D Fourier transform of that, it looks like just the artifact part that we were sort of bothered by in the previous image. Whereas the top stuff, when we take the Fourier transform, when we have the object, we acquire the K data, take the Fourier transform, we just basically recover the image of the object. So it's the superposition of these two things that gives us the static image that we want, but also this flow artifacted component on top of it. And so it ends up looking like this. So interestingly, well, let's think about it, right? What kinds of things govern how far apart these artifacts are? They could be closer or farther apart, right? So what about our object or our acquisition governs how close or far apart those things are?
Frequency of object.
Yeah, so the frequency of this object plays a big role, right? How quickly it's getting brighter and darker, right? If it's entirely bright or entirely dark, those are extremes, and then there's all kinds of frequencies in between. And so basically your heart rate, right? It's going to govern in part the periodicity of what's happening over there. But it's also related, that's one component of it. What about our K-space acquisition governs the frequency of that artifact? So we have a frequency or a time component associated with physiology, right? What about my K data? Yeah, what about it though? What about the acquisition itself plays a role in the frequency or the periodicity of the artifact? Yeah, it's related to the TR for sure, right? Because the TR basically governs how fast I move across K-space, right? So every TR is typically a line of K-space, right? So if my TR was picoseconds, right, then I would just zip through K-space, and I would just capture this object in one of its states, and it would just have that according, have the right orientation and the according intensity in the object without this sort of artifacting. But because my acquisition itself is relatively slow, and it's slow on the same time scale of our heartbeat, then we get these banding patterns. If I zip through K-space really quickly, then the periodicity between these things gets farther and farther and farther apart until it's gone. Right?
So this ghosting would be considered a form of aliasing?
I don't think of it as an aliasing artifact, although in some sense it is sort of an undersampling artifact. We usually just refer to it as a ghosting or a flow artifact. Okay. Right, and that's just showing the superposition of the two. Okay, so what can we do about this? Well, we talked about one of these already. One was cardiac gating, synchronizing the imaging system to the heart rate by using the ECG. Holden and I know will give you some examples of sort of how we practically do that. Another possibility is actually methods that will help you suppress the signal from moving or flowing tissues. I didn't put those slides in here, but we talked about having spins that flow into the slice. They're brand new and they're fresh spins. There are techniques to saturate the spins before they get into the slice. So we can play a saturation pulse, for example. We can play this 90 pulse, and when they get into the slice, they're saturated, or we can make it such that their transverse magnetization is very, very low. So there's different ways of dealing with the moving spins themselves as well. And then as this was a phase encoding artifact, right, it sometimes helps to change the phase and frequency encoding directions. And so the example I was showing you was through plane flow, right? Well, actually, just go back to it. And so this example here, we were picturing, at least I was describing the flow that's exactly through the slice this way, right? So we understand from the previous example that we have a frequency encoding direction, we have a phase encoding direction, and this is again a phase encoding artifact, right? It doesn't show up in the frequency encoding direction. What happens to my artifact if I swap the phase and frequency encoding directions? What if I start doing phase encoding left-right? What happens to my artifact? Stay the same? So we said this is a phase encoding artifact. It has a relationship to the direction in which I'm doing my phase encoding. Yeah, and so if I start phase encoding left-right in this direction, then this flow artifact will swap to this direction. That may or may not be better for the purposes of the artifact. Usually we care about artifacts because they interfere with measuring something or seeing something that we really care about. Sometimes it's good enough to just shift the artifact. So just by swapping phase and frequency, we can shift the artifact to be perpendicular, flips over to this direction, and maybe that's good enough. Sometimes in doing so, because of the specific direction of flow, the artifact can actually get smaller. If the flow was actually sort of like in this direction versus in this direction, sometimes you can minimize or mitigate that specific artifact as well. Obviously, disadvantages if you're going to use things like cardiac gating or some kind of respiratory navigation, that's going to, in some sense, increase your total scan time. Increases to the TR can help, although faster imaging is usually going to be the thing that gives you the smallest artifacts. I'm not positive what I'm trying to get at there. What did she say? I guess maybe by changing the phase and frequency encoding direction. That's okay. We'll sort that one. Okay, so that's a very high-level overview of sort of how motion can lead to artifacts in MR imaging. And then I think what we'll do is we'll talk through data clipping and then possibly take a break. So what is data clipping? You have to imagine you're acquiring K data and that signal that you're trying to receive, it's a voltage induced in your coil going to some long receiver chain. It's possible that that received signal, that voltage, could saturate the receiver. We have to set the receiver gains appropriately. And the scanner does a lot of calibrating and buzzing and clicking to set those gains appropriately. But it's possible that things don't go perfectly. Obviously, we usually have the peak signal usually in the middle of K-space. That's our brightest, highest intensity region, because it's the middle of K-space is really telling us about the total amount of spins, right? The volume of spins inside our excited region. And so, in the peak signal being in the middle of K-space, if there's an artifact or a problem in the middle of K-space, that's going to have an effect on the low spatial frequency information. And the low spatial frequency stuff is related to overall image contrast and overall image intensity. So if there's some problem with accurately recording the center low spatial frequency parts of K-space, you'll get some funny contrasts or some funny intensities. Again, there are pre-scanning procedures that usually avoid the so-called data clipping by adjusting these receiver gains. If it doesn't happen, here's the possible consequence. So here's what your K-space data should look like. And picture it like, like a mountain, right? It's tall in the middle and falls off to the other side. If I take the 2D Fourier transform, I get an image like this. This looks, for what it's worth, kind of photon density weighted. Now imagine that my K-space data that I acquired, it's supposed to be a mountain, but now it's more like a mesa, right? It's been chopped off at the top, and all of the signal intensities at the top are effectively the same. Then you get these really kind of hazy artifacts across the whole field of view, disrupting, obviously, the overall image contrast as well. It's not a very common artifact anymore because these systems are pretty good at adjusting appropriately, automatically adjusting the receiver gains. But it's another example of, were you to ever see an image like this, it's helpful to think back to how could that possibly happen in K-space. And you should begin already to have some ideas, right? That when you see an image and you see an artifact, how does that connect back to k-space? One of the other sort of obvious examples we've given is like point or spike artifacts, right? And so this is sort of, in some ways, related, but quite different artifact. It's just called data clipping. Lots of artifacts in MR, right? So one more that we'll talk about is what we call radio frequency interference. And so depending on the system that we have in mind, right, it's either a 1.5T system or a 3T system, there's a specific and relatively narrow range of frequencies that we really care about. The Larmor frequency plus or minus, a couple hundred millihertz. So radio frequency, or the RF fields that we use are really close to, example, FM radio stations, right? And there's a lot of stray electromagnetic radiation in our atmosphere that's just bouncing through this room right now. We just typically don't care that much about it. And so what's needed, though, is a way to shield local sources from interfering. So there's some source of electromagnetic radiation. There's a broadcast antenna next door or some other piece of electronics. That EM radiation will get into your MR room, right? Why wouldn't it? You get into this room. And if it's at the right frequency, close to your Larmor frequency plus or minus a couple hundred kilohertz, your coil will just pick it up. And it's just information, right, that could be received. So how do we avoid that? Well, we talked about this, probably in the second lecture, where we can copper clad the entire room, building a so-called Faraday cage, so that stray electromagnetic radiation is effectively trapped by this Faraday cage. And yet, we still need to be able to get certain signals in and out of the MR room, right? We have to get the gradient currents in and out of that room. Otherwise, we have to put a giant gradient amplifier inside this room, and it generates EM that gets into our coil. So we try to keep almost everything outside of the room and then pipe it in sort of appropriately. One of the ways that things get into the room is through the so-called penetration panel. So if you start working in a clinic, working as a medical physicist or as a scientist, we oftentimes have to get signals in and out of that room, but there's a good way to do it, which is through the so-called penetration panel. We won't get into the whole details here, but this is just a drawing of one of the ones for one of our instruments. And the point is that cables going in and out need to be filtered before entering that suite. We don't want a cable to be carrying in stray EM that will then get picked up by our MR coil and somehow end up on the bridge. So that's sort of the physics behind why or what could happen with radio frequency interference. The artifact is pretty discrete as well. And so if we have a so-called RF leak, there's a reason, some great reason that RF is getting into the room, maybe because your scanner door is wide open, someone is running wires in and out of the room that are filtered, or the room shield itself becomes faulty. And that happens in rooms that have been in place for a long time. The copper shielding can get moisture over years and start separating, or there's some leak that no one knows about, or whatever. Unfortunately, the consequence is you get these really kind of distinct striping or banding artifacts in your images. Obviously distracting, obviously not good for overall image quality. There was, when the Reagan Hospital first opened, which is already about 8 years ago, one of the scanners there had an RF leak for about a year and a half because no one could decide whose fault it was, right? The people that built the RF cage said, we build really great RF cages, it wasn't us, right? And then someone else said, well, it wasn't us, we didn't hammer nails through the RF cage, it was that guy that hammered nails through the RF cage. So anyway, it took a long time to resolve. For literally probably a year and a half, almost every image coming off that scanner had that artifact. So the clinicians got really good at just reading right through it, right? Not so that, right? Okay, so here is, I also like asking questions like this on the final, because artifacts are really important to know. So the left-hand side is the object, right? This is what we think this whole thing should look like. You're going to do a lab on Wednesday, actually, and you're going to, when the protocol is first run on the object that's in the scanner, you don't know what the object is, you don't really know what you're even supposed to be getting to begin with, but you will get images that are far worse than this. And it's a puzzle, right? You have to start telling the TAs what you think is going on, and you will do the troubleshooting. They'll run the scanner so that nothing terrible happens, but it'll be up to you guys to figure out how to solve this problem, right? So we can do one right now, right? And so this image on the right-hand side has a bunch of different artifacts, right? Some are maybe easy to identify. I know what they are because I made them, right? There was a way, this is a synthetic object, and I can manipulate the fields and do everything I want to make this artifact, or this composite image with several artifacts. So let's just go through it. Who wants to pick out an artifact and maybe describe something about what they know about that artifact? There's a couple easy ones. Yeah.
There's a motion artifact. You can tell because there's a couple bands that are above the top of the image. So
Yeah, so you do, yeah, so there's, it looks like there could be some motion artifact you're picking up on these artifacts here, right? And we said that motion artifacts usually appear outside of the object. So that's one pickup. Yep. Okay, and why do you say that? Right. Okay. So what? So you're right. There is a B field in homogeneity, but what field is it that's causing it? What if I said it might be a different field? What if it might be a different field? No, you're totally picking up on it in terms of seeing the artifact, right? And so I want to see if I can sort of tease it out, right? So related to that artifact was this other thing that we see, right? So you called it bow-leggedness. Absolutely, it has this kind of bent look to it. There's also no imaging data sort of in the corners there, right? What causes that? You had a homework problem that was partly related to it. Gradient what? Gradient nonlinearity, right? So if your gradients aren't perfect, we don't get this linear mapping of frequencies with position, and we get this bow-leggedness. And then the scanner will say, well, we know our system is not perfect, and so we'll bend the images back to the right geometry. When you bend the images back to the right geometry, then you don't have the ability to produce imaging information, for example, in the corners, because you have to squish the image back in some sense. So this is an image actually that needs to be squished the other way, right? Because it doesn't have the geometry that matches the underlying geometry. Okay, so 2 down, but there's like 4 or 5 to go. What else? Yeah. So certainly you're pointing to this stripe right here, right? And we just went through RF leaks, so we don't have to say too much about that one probably. What else?
Saturation.
Yeah, something's going on. What do you see? What do you
There's
notice?
just kind of staticky noise and signal throughout the whole thing. There should be black on that outside.
Okay, so staticky sort of noise and signal sort of on the outside. So we don't expect to be perfectly zeros, right? Like that would be unexpected. I think what you're picking up on is that the background signal here is sort of also non-zero. Noise is an artifact, right? We don't want noise, and clearly the whole image has noise. So we don't always think of it as an artifact for some reason, right? But it's undesirable. It's an undesirable image feature is an artifact. Yep. Yep. So good pickup. So what you're identifying is this really bright ring on the outside here doesn't have the same physical correspondence that we expect. It should just be immediately adjacent to sort of this underlying tissue. But that brightest ring is obviously shifted to the right. So that's a good pickup. What does that tell you about your phase and frequency encoding directions? What's your frequency encoding direction? Chemical shift is a choice? Almost. Chemical shift is something we generally notice during readout, right? And so what's our phase? What's our frequency encoding direction? Yeah. So frequency encoding is what? Sorry. Left right. And so you see chemical shifting left right. That's a readout encoding artifact. And so we know our readout encoding is left right because our chemical shift is left right. Okay, so I forget. I've lost track of that's 4 artifacts maybe. There's at least 2 more. Yeah. What do you notice? Yeah. And so this is a kind of a tricky one, right? So you're picking up on it for sure. It's obviously bright, sort of top left, and getting a little darker as you get to bottom right. Different things could cause that. Which one did you suggest? You said B, but I forget which B. It doesn't have to be B. It could be something else. we actually saw some examples of this kind of in maybe the last lecture. Someone that's not Tyler. Yep.
Does it have to do with coils?
Yeah, right. So what do you think's going on?
Well, in the one we saw where it like made the image, there were coils all the way around, kind of
Yeah.
like you could assume.
Yeah.
But it obviously they favor what they're closest to. So
Yep. Yeah. So what do you think is happening? Obviously, things are sort of darker down here. So what do you think is going on down there, for example? We have all these. We potentially, I think what you're drawing out is we could have coils in lots of different places, right? We have 8 coils surrounding the object, right? Sure, maybe, right? And so we have these coil elements. When you go to the scanner, you can control the coil elements. We put on a head coil, and we just call it a coil, but the coil has lots of channels. And at the console, you can control which channels are on or off. And there's different reasons you might do that. You might load up the patient with a bunch of coils because you're not exactly sure if you're going to do sort of abdominal imaging or if it's going to be a little more north, so you put on some more coils, fine. But you don't want to receive everything from all of those coils. It'll be a ton of data, and it won't necessarily improve your image quality having a coil that's distant from the underlying object. So you could have a faulty coil. The coil itself could be busted in some ways. That definitely happens. The other possibility is that it's just software control. The channel was turned off during the acquisition. There's at least one more.
Okay, so also, if we've already discussed that there's like motion,
Yeah.
because there's ring outside of the object,
Yeah.
how do you know if there's motion or motion and Gibbs ring?
Yeah, no, it's a good question. So it's pretty subtle. So this artifact actually is a Gibbs ringing artifact. So I probably thought that, and maybe it's not exactly true. I guess you can have some Gibbs ringing that's partly apparent outside the object. So I guess I'm probably not quite right about that. This is a Gibbs ringing artifact. So Gibbs ringing artifacts happen in the phase encoding direction, which is our lower spatial resolution dimension, and we have a really high contrast boundary. A motion artifact, if we just went back like 6 or 8 slides, could look a little bit like this. Typically, you'd have sort of the concentric artifact. The artifact would be concentric over larger parts of the object, and you would see it throughout the object as well. So sorry if I didn't pick up on that exactly that way.
On the right, you have black and
On the right.
canceling out the signal.
Are you thinking about sort of this right here?
Yeah.
Yeah. So what is that?
Real is called, but that's because you have 2 signals that are closer to her, and they're
It can happen because of that, right? So if we have in phase and out of phase stuff, right? So that's chemical shift type 2. That could happen. In this case, all that's happening is you have this really bright ring. Imagine that really bright ring is fat. When fat shifts to the right, it just leaves a void, right? There's nothing else to fill in this gap over here. It shifted to the right, the fat went to the right, but it just moved away from the underlying water signal. And on the right-hand side, you can see the fat just superposes with the water signal, adds up. So that's a possible artifact, but because I know how I made this, it's not specifically what's happening. Okay, that's good. So you'll play with this in real life on the scanner, and then I think it's fair game. Or these kinds of questions are fair game. We're trying to understand what's identifying artifacts and then describing sort of what they're all about. Any of the things that we've done. Let me take a quick peek here. Yeah, why don't we take a quick break because it's 5, and then we'll come back and get through whatever it is that we did.
your stuff's unfiltered.
Stop.
It's the fountain.
It's
I
not,
turned it off on my rover.
it's not filtered.
No, it's
Oh,
done
okay.
filtering.
Okay.
Yeah, just like that black goop left. Is that just fresh blood? Is that why it's
Oxidized.
yeah.
Unplastic.
Yeah, it doesn't come out that way with the
Unplastic.
and what oh yeah. What was wrong with it?
Maybe
What kind?
mucoid. It's cultured egg.
Yeah, yeah.
3D printers here.
It's here.
Like it's in CHS.
Yeah, yeah, okay, right, yeah.
It says delivered.
Let's track it down.
Yeah, tomorrow's yeah.
Yeah, yeah. Let me put it
Should already be built.
Yeah, it should be. Yeah, we should talk. Yeah, we can. That's right.
I think Jessica needs to print something on it.
As long as it doesn't. As long as it's not.
Let's see how loud it is. But it shouldn't be.
No, but sometimes it's just enough.
Yeah. I
There's
mean,
that one small movement.
I think there's one part that's coming sometime this week.
Oh, just like.
And they accidentally sent us the wrong one. They sent us 5 filaments that were wrong off the original sheet, but they sent us a prepackaged label. We'll send it back and they'll just swap it out. It's easier than having to redo everything.
Yeah.
Heart rate was way up. Respiratory seems fine at the moment. Today, respiratory was a huge problem. Because there's fine halfway through the cities, and then, you have to go in there and fix it, but then that increases the heart rate. And then if they increase the heart rate too much, then your images are going to be a little bit off. And also the scanner needed to reboot. With no got reboot this morning.
Yeah. No, that's probably. All right, let's go ahead and wrap it up. We've been talking about artifacts so far, and what we're going to talk about now is getting into some faster imaging topics. Just a couple tricks that we can use to image faster. And there's a lot of possible tricks when it comes to fast imaging, and I've said it twice already, but Pung's lecture will address this even more so than this lecture. So an interesting idea, or an interesting concept that comes up in MR is this idea of what's called Hermitian Symmetry. I should probably jump to this slide first. So Hermitian Symmetry, you might have noticed already, when you look at K-space, there's some symmetry in this K-data, right? And a point in K-space that's top right, positive quadrant, according to the Fourier transform, should have a conjugate pair in the in the minus quadrant. And so if you look at sort of the pattern that's happening in K-space here, you can picture that looks to be approximately the case. But of course, MR systems aren't perfect. If you take the Fourier transform of a real valued object, it doesn't have imaginary components, you take the Fourier transform of a real valued object, then the Fourier transform itself will have and share Hermitian symmetry. We would like that to be true of our MR imaging systems, but it's not true for a couple different reasons. So going back a slide, if our object, our our I of x, if you will, some image as a function of some position or some value as a function of position. If it's real valued, then its frequency representation, what we usually call S of k, is actually redundant. So if your S of k is known for k greater than 0, say the top half of k space, then your S of k for k less than 0, the bottom half of k space can just be generated, right? We can actually just get that from the existing data because of these conjugate pairs. And this is the idea that k space should be, Fourier space is Hermitian symmetric. It would be nice if, in fact, our k space data was perfectly Hermitian or conjugate symmetric, but unfortunately, it's not quite the case. And so, if you look at an actual, data acquired at this k point, and it has a magnitude and a phase, right? It's complex data, and you compare that to the data at this point, they of course won't be identical, and they won't be identical for a bunch of reasons, which we'll talk about. So every point in k space, every of those entries in the matrix has both a magnitude and a phase. Conventionally, everything that we look at is really just the magnitude. We use that as sort of just like the representation of k space. We haven't really talked too much about the phase. We remember that in the object space, so not k space, but back in the object space, that the transverse magnetization has a magnitude, but it also has a phase. Right? The magnetization could point in different directions. And in fact, on the Tuesday lecture that's coming up, Mike will talk about how we store information in the phase and how we can use that as it can be a very useful component to the MR experiment. And so he'll get into some more details about that. So bottom line, every point in k space actually has a magnitude and a phase. So what if our object itself is real valued? So a digital object, something that you make in MATLAB, is inherently real valued unless you add a phase or make a complex value on purpose. But objects, things sitting in this room, they are in principle real valued to begin with. If that were the case, meaning if our imaging system didn't somehow corrupt that signal a little bit, then we would really only need to acquire the top half of k space. And so that sounds appealing, right? Because we could acquire half of k space and obviously scan twice as fast. You'd have a signal-to-noise penalty for doing so because your scan time was cut down, but you would be scanning faster. So in principle, it sounds like a possible or appealing thing to do. Unfortunately, it shouldn't be a question mark, but our objects aren't real valued. Rather, the objects themselves are real valued, they're real objects, but after the receiver system gets a signal from the object, that signal will become complex valued for different reasons related to mostly the receiver chain and some other things. So unfortunately, again, our imaging system adds some phase, and it takes a real value, what should be a real valued object, and will turn it into, if you will, a complex valued object. And so the data itself becomes complex valued. And the phase that's added to one k point, so if we think about being a positive kx, ky point in k space, we've acquired that point of data, and now a little bit later we're getting down to the minus kx, minus ky point of data. There can be a different phase corruption to this k point relative to that k point. They're both imperfectly acquired, and they both have some additional complex value added to them, but we don't know which one, we don't know which answer is quite correct. That happens because of noise. Obviously, the instantiation of noise for every k point is going to be slightly different. In fact, it can happen because of motion. So if we saw sort of artifacts as a consequence of motion previously, those same sources of motion can add phase to the signal. And since the motion sort of has this funny correspondence to where you're acquiring or when you're acquiring your k space, the amount of phase added to a k point can be different depending on the underlying motion pattern. You can have things like resonance frequency offsets that occur during the acquisition, so-called hardware group delays, meaning that you're acquiring data at the beginning of k space, but there can be delays in this acquisition system, even at the scale of microseconds or less, that will cause small discordances in your acquired data. And then something we haven't talked about too much, I think Mike will talk about this a little bit in the phase contrast lecture, but there are others. We saw one example of this right in the lab of eddy currents, right? The aluminum board that was falling towards the scanner. Well, anytime we turn on the gradients, we can induce currents in conducting structures somewhere in the scanner. Conducting structures generate fields, those fields generate offsets, and those can cause problems. We refer to those as eddy current-induced fields. Point being, there's lots of possible reasons that one, for a Hermitian conjugate pair, one k point of data will have different sources of errors and artifacts than another point in k-space. So we don't know what the sources of error are, so we can't really resolve which of these two k points is more reliable than the other, and consequently they just are different. Like I said, I didn't get this one, but coil phases. Remember that the coils themselves don't just color the magnitude, something that we saw in the artifact that we were just looking at. But if they can manipulate in some sense the magnitude of the received signal, they can also add phase, and they might add slightly different phase to different k points. So, so the point, I guess the point of that is that we can't actually just acquire half of k-space, and yet there are ways to scan a little bit faster using so-called partial Fourier acquisitions. And so here the red lines, solid and dashed lines, are supposed to represent, some of the k-space that's acquired relative to the background magnitude k data, which is supposed to be sort of all of the k data. And so there's two different possibilities here. On the left-hand side, we have what's called partial excitation, sometimes called partial nex. It's a partial Fourier acquisition strategy where we're getting, say, the top 3/4 of k-space, but we're not acquiring the bottom quarter of k-space. The other alternative is so-called partial Fourier or partial echo or fractional echo acquisitions. So on the left-hand side, we're just choosing not to acquire these k data. And we won't get into the reconstruction methods in this class. They'll pick that up in 229. But there are good ways to estimate this data if you have, say, more than half of k-space. And the reason for that is you can generate a low-resolution image from the middle of k-space. You have all of the data in the middle, so to speak. That's low resolution, but these background effects that we were talking about tend to be kind of low-resolution things. They're not really changing at high spatial frequencies. So we can use the top data here to help inform or estimate the bottom data here. So what impact does this have on scan time? Up or down? Down, right? We haven't acquired as many lines in k-space. Obviously, we can scan faster. That also has a consequence on our signal to noise, right? So for this kind of acquisition, is our signal to noise up or down relative to full k-space? Down, right? What about our voxel size? Have we changed our voxel size or our pixel size? By not acquiring these lines down here? Yeah. So we still have high spatial frequency data. We just didn't get its Hermitian conjugate pairs, right? But we still have the same resolution. So in principle, resolution is maintained. We're just scanning faster. So this is a pretty simple fast scanning approach. Just asymmetrically acquire data in the phase of co-direction. And you can go 25% faster, all the way up to, but not quite, say, twice as fast. Right? We need to have a little bit more than half the space. So that's pretty good. A different approach is what's shown on the right-hand side here, right? So this is what we call partial or fractional echo, right? How do you think I acquired that data? What do I have to change about my, let's say it's a gradient echo sequence, right? What do I have to change about my gradient echo sequence if that's the trajectory of the k data that I want to acquire? Your TE is going to change, right? So if this is the beginning of readout, I'm still forming my echo in the middle, this point here, but the time from the beginning to here is obviously shorter than on the left-hand side, so my echo time will shorten. What's the advantage to a shorter echo time? More signal. Why?
Because it hasn't had T2 or as much T2 decay.
Yeah, or if it's gradient echo, T2 star decay. Yeah, and so shorter echo times are better. We want short echo times in general. That being said, we manipulate our echo time to control T2 contrast. So there's always this balance between high signal, which might be what you need, or contrast, which might be what you need. But in terms of the gradients, remember the gradients move us around k-space, right? So when we had our, let's just think about this middle k line where there's no phase encoding happening, right? So now we're just thinking about the readout gradient, right? And the readout gradient, sorry, I'm gonna draw a readout gradient for conventional gradient echo looks something like this, right? Where if this was area A, then this is area A, and this is area A. And in K-space, that meant that I would move out, you know, a length, I don't quite want to call it A, maybe little a, and then I would turn around and go the other way, a distance A and a distance A, right? So this is the gradient waveform that corresponds to that trajectory. And that trajectory would be, say, acquiring this line here, right? So how do I do that? What do I have to do differently?
This area in the negative.
Yep. And so maybe this first gradient here, I could draw it different ways, but if that first gradient is shorter, right, so maybe it's A by 2, then I'll only go out half as far, and then I'll form my echo again at A by 2, but if I want to get all the way across K-space, I still have A. So the K-space trajectory here would be to go out a distance here, A over 2, and then turn around and read out this way, a distance A over 2, and then distance A. It's a good idea to be familiar with how to go from a K-space trajectory to a gradient like this, or how to go from a gradient like this to a K-space trajectory. I want you guys to have that connection. It's just through an interview, right? Like that's ultimately all it is. But it's good to test yourself on that. I like those questions. Okay, so I think we kind of talked about this. So there's a way to play the gradients to do this acquisition, and the advantage would be a shorter echo time, which could give you more signal, although it would also adjust your contrast. So on the right-hand side, this really isn't a fast imaging technique per se, right? It's not saving time. You have just as many echoes. You might if you tighten up your echo time, you have a shorter TR, so maybe that's a little bit of a benefit. But as most of your time is associated with how many phase encode lines you have to acquire, there's not much of a difference in time between those two acquisitions. Okay, so probably this we already talked about. In the readout direction, you can do this partial Fourier acquisition to reduce the echo time, improving the signal to noise, decreasing T2 star decay. Not quite as obvious. We'll talk more about gradient moments. Gradient moments are related to the integrals of our gradient waveforms. Mike will talk about this in the flow lecture on Tuesday. But we can control how flow appears in an image, and we can control how we can measure flow in images through so-called gradient moments that are related to like the statistical moments or the gradient areas themselves. And then in the phase encode direction, obviously, if we cut it down in a partial Fourier sense, then that's going to help us reduce acquisition times. If we do partial Fourier, what are some of the disadvantages? Well, anytime you're scanning faster, you're going to take a hit in signal to noise, right? The trick is to kind of balance that, to go as fast as you can with acceptable signal to noise. The simplest reconstruction for that partial Fourier data is just zero filling. I didn't have a good example. I couldn't find a good example this afternoon. The result of zero filling all by itself will be that your data will actually be a little blurrier than it could be if you did a smart reconstruction. We won't in this class get into sort of smart reconstructions, more complicated ways of synthetically building that missing K data, something smarter than just zero filling. There are a bunch of methods for doing that, and they might increase the scan time, not really a big deal. They will have a little bit less blurring, but there's still some residual modest blurring associated with having that missing, say, higher spatial frequency data, even though you have the other side. Okay, so this is kind of switching gears a little bit. This is a very different sort of fast imaging technique. But what I like about this is it's kind of clever, and it shows sort of some of the flexibility that's possible with MR. And so let's think about this acquisition here. So this is a spin echo acquisition, right? It starts with a 90-degree pulse that's slice selective, has a 180-degree pulse for refocusing, and then we more or less can quickly form an echo, right? Adjusting our TE for T2 contrast, adjusting our TR for T1 proton density weighted contrast. That's all great. So we pick our TE and we pick our TR for contrast, right? That's what gives us the image quality that we want. But once we're done acquiring our echo, we're done, right? We've measured and written to disk the data that we care about. and now there's so-called wasted time, right? Now, that time's not really wasted, we need it, right? If we tighten this up, right, if we pull the 90 all the way across to bump up close to the end of the readout here, we're going to change the image contrast, right? So for lots of protocols, we pick the TE, we pick the TR for the image contrast we want. Nevertheless, because we're waiting during this interval for magnetization recovery, right, MZ is just growing back this entire time. Transverse magnetization is just decaying the entire time, and for whatever contrast we were trying to get, this is the chosen TR, and this looks in some sense to be wasted time, except for that there's magnetization recovery. So the question is, could we be doing something else? Fine, the magnetization needs to recover, but could we be doing something else during this wasted time? And of course the answer is yes. So this is pretty clever. And so this principle of slice interleaving looks as follows. We basically excite, refocus, and read out for slice 1, right? Slice, excite, refocus, read out. You have your data, right? So let that slice recover, let it regrow, or let the transverse magnetization decay, let the longitudinal magnetization regrow, and just go visit another slice. Turn on the same slice select gradient, change the center frequency a little bit, move that slice down, excite it, refocus it, and grab the echo. Right? That echo is only going to come from the excited slice. This is magnetization that's recovering. The transverse magnetization is decaying, longitudinal is recovering. Let's go visit another slice. And in fact, if you have enough time, enough wasted time, then you can go visit slice 3 or 4 or 5 or 6. And so this approach actually works up to many slices. And so in this example here, how much faster can I effectively go? In some ways, it's 3 times faster, right? Now, the trick is, it's not 3 times faster for slice 1, right? Slice 1 still has the data rate is the same. It's just that while I'm getting slice 1 or waiting for it to recover, I snuck over and got part of slice 2, and then snuck over and got slice 3. So it's 3 times faster in that I got 3 times as many slices for the same scan time, right? And that's good. I mean, oftentimes we need coverage. We want whole brain coverage, or whole chest coverage, or a whole knee coverage. And so almost all of our protocols are multi-slice. And so this is a nice approach to what we call slice interleaving. And so if you think about scan times for this, right? So this would just be what I call sequential 2D imaging. Get a line of K-space, wait TR, get a line of K-space, wait TR, line of K-space. And so our total imaging time looks something like this. It's our TR times the number of KY lines times the number of slices. And this can build up, right? Even if our TR is what sounds short, like 100 milliseconds, if you have hundreds of lines and dozens of slices rather, this can easily be 10 minutes or 20 minutes. And it's almost surprising you can get out so fast, but it definitely can. So we don't really want to do sequential imaging in general. And so then this is just showing the approach we were discussing before about slice interleaving. So we can get a line for slice 1, a line for slice 2, a line for slice 3, 4, etc., and then move on to the next line and repeat it back to the first slice. And so the advantage here is that your total imaging time still depends on your TR, still depends on the total number of lines and total number of slices, but you can divide by the number of possible interleaves. You might be able to get 3 slices in the TR, you might be able to get 12 slices in the TR. And so that you get a big reduction in that sense to total scan times. Kind of clever, right? Just always thinking about, and we still use these kinds of principles, looking at pull sequences, trying to figure out what way they're inefficient, and try to use that time in a smarter way. So I like this as a fast imaging example, just simply because it's faster, because it's clever. Okay, so what's the advantage? Well, obviously we can scan faster, that seems great. Disadvantages, you can only scan so fast, right? The number of interleaves, the number of slices you can visit is limited by something like the TR divided by the echo time. There's a max number of slices you can squeeze into that TR. And you may, in fact, run up against SAR issues, right? Now you're blasting 90s and 180s sort of continuously. You may bump up against a SAR limit where you have too much energy deposition for the patient, and so you can't get that many slices, say, per TR. A very sort of not entirely obvious thing, we talked about this a little bit about slice profiles, right? When we excite with the 90 pulse, we're exciting a certain profile for that slice. We want it to be a rect profile, but it won't be because our pulses are finite And in fact, when you look at designing a 90 pulse, it has one slice profile. And then you go design a 180 pulse, it has a different slice profile. And those differences will give you some artifacts. So it's really hard to get that 180 slice profile to match your 90 slice profile under any circumstances. And as a consequence, you'll get artifacts from one slice that are leaking into an adjacent slice. Lots of different applications, but principally they're going to be for pulse sequences that require or need a long TR, right? So it's sort of here already, but T2 imaging requires a long TR, right? Why? Why do we need a long TR? TR is this like T1 over TR term, right? T1 over TR. Why do I need a long TR for T2 imaging? Makes sense? This goes back 6 weeks. So the way I think about this is the TR terms have T1 components, right? They look like T1 over TR, and I want those T1 over TR terms to decay, right? If those T1 over TR terms are strong, then they're adding to my signal, and that means I'm getting a T1 component in my signal. So I want long TRs so that T1 component fully recovers or doesn't contribute to my T2 signal. And so T2 imaging, if you want pure T2 weighted images, you typically need very long TRs, right? What's a long TR? What's a long T1 for us? Just ballpark. What's a tissue? What's a T1? What's long? Fat? Fat's short, right? So short for us means 100 milliseconds, 250 milliseconds, something like that. So what's a long T1? CSF. How long? Perfect. So CSF, long T1, 2400 milliseconds. And so if we want that signal not to kind of bleed back in, we have to have very long TRs, like 4 or 5 times the T1 of CSF. That could be quite, 10 seconds, right? We can manage that. We might not choose to have it be quite that long, but it indicates that it needs to be long. Similarly, we haven't talked about, I think Ben Alling said in the last lecture we'll cover this, which is diffusion-weighted imaging. MRs, I find it totally amazing, but it can be sensitive to the self-diffusion of water, how easily or not water molecules move around in soft tissues. It's another example of typically needing a long TR for signal recovery. And so again, multi-slice 2D imaging, absolutely. Multi-slice DW diffusion-weighted imaging, absolutely. It doesn't tend to work quite as well for T1 weighted imaging because why? Why don't we typically use this for T1 weighted imaging? Because our TRs are too short, or at least short, right? So you might be able to sneak in a slice or something, or even a couple, but it doesn't have the same advantages it does for T2 imaging, where you can have even a dozen slices or more and go around faster. Okay. I think I'm going to leave this as an exercise for you guys. Maybe I'll start it so you sort of get the handle, because this will be a good thing for you to go through before the lab on Wednesday. So I'll get you going with this. You'll see what it looks like in just a second. But you're going to want to use some of these principles in the lab on Wednesday. So I think this is a good way to get ready for the lab. So here what we're thinking about is protocol optimization for fast scanning, right? We always want to scan faster, but we need to reach or achieve a certain image contrast. And so here I start off with what I call the infeasible protocol, right? So let's think about a T1 weighted gradient echo sequence, right? Sort of bread and butter, T1 weighted gradient echo. How am I going to achieve that? Well, this will give me T1 weighting, kind of intermediate intermediate TR, pretty short TE, and a sort of intermediate flip angle. That is, if you go back to the GRE signal equation, that will be a T1 weighted signal. Okay, so that's a good starting point. And now I pick my matrix size and I pick my field of view. Pick a field of view big enough to encompass my object. In this case, this is big. This is almost 50 centimeters by 50 centimeters, right? Most of us will fit into that field of view pretty well. And let's say I choose a big matrix, 256 by 256. What's my resolution? My resolution is going to be okay. It's going to be 2 by 2, almost, right? And maybe I choose an 8mm slice. Unfortunately, my acquisition time is going to be about 43 seconds. So if I multiply my TR by the number of phase encodes, it blows up a little bit. Not a lot. 43 seconds isn't too bad. But if this is supposed to be a chest or abdominal protocol, I'm going to have respiratory artifacts, right? No one, well, I don't know, we could try. You want to try? Who can hold their breath for 43 seconds, right? Some of you can, I guarantee it. But we don't typically want to do that, especially for our patients, right? So if you were to pull up this protocol on the scanner, it would report an RSNR of 1. I've chosen to call it 3.4 because we're going to work towards a protocol that will be 1, and then we're going to go past that also. This is just a relative signal to noise. It's arbitrary. It's a number that's based on that SNR equation you saw earlier about voxel volume and scan times, right? The scanner can calculate that very quickly. It doesn't do block simulations. It's not trying to figure out real signals and measure noise or anything like that. It's just giving you some insight that if you change a bunch of parameters, is that protocol likely to have better signal to noise or not in the protocol you start with. So this is the baseline setup. Does that seem fair? Does that seem pretty straightforward? So I'm not saying this is a good, actually, I'm not saying this is a good protocol or a bad protocol. I'm saying it's an infeasible protocol. It's terrible, right? Mostly because the scan time is too long. And in fact, I don't think the resolution is that great either. So let's see what happens. So what's going to be the problem? Well, patients can't hold the breath for 43 seconds, so you're going to have breathing motion. The advantage might be that you'll have abundant signal to noise. Let's say our target signal to noise is an R signal to noise, relative signal to noise of 1. So this is actually kind of too good for what's required for image interpretation, but obviously the artifacts can totally kill all of that. Obvious disadvantage, scan time is too long, and in fact I think the resolution isn't really all that great. So here's an example of how this could potentially look. So here's an image acquired with that protocol with a subject who chose not to hold their breath for 43 seconds, right? And representationally, I'm showing a bunch of case-based data on the left-hand side. So what I'm trying to show you here is that there is K data, again, in the background, and all these little circles represent, they're just a sort of a cartoon example of the K data that I might have acquired to get this image here. And then what happens, we'll work through one of them, maybe two, but there's 5 or 6 examples that sort of make adjustments to the protocol and try to improve the overall image quality. And so you'll see the K data here is I'm going to get more of it, I'm going to get less of it, or I'm going to spread it out. It's going to change my field of view, it's going to change my resolution, and it'll have impacts on my image quality. So this is sort of the starting point for this exercise, right? Good? Okay. So let's make some changes, right? So the infeasible protocol. We didn't like our field of view. It was really big, right? If we go back a slide, you guys have it in front of you here, right? My field of view is bigger than I need it to be, right? You can tighten up your field of view for sure. You can certainly tighten it up AP, right? You don't need to just fill all this void space. That takes time to acquire. And you can tighten it up left-right. What's the phase direction, phase encoding direction for this image? Yeah, see Hayden pointing up and down like this, right? So phase encode direction is up and down. You can see this respiratory motion artifact throughout the object, outside the object. And you can pick up some pulsatile artifacts from the aorta, the ascending and descending aorta as well. Mostly this band, and then probably up here as well. A little subtle, but definitely. Okay, so we know the phase encode direction is up-down, but and so that's helpful. The frequency encoding consequently must be left-right. In the frequency encoding direction, remember, I can shrink up my field of view without aliasing artifacts, right? So I can make this not quite arbitrarily smaller, but smaller. And for example, chop off the arms, and that won't be an aliasing artifact because this is the frequency encoding direction. Aliasing happens in the phase encoding direction. If I make my field of view too small, then I'll have aliasing in the phase encode direction. So there's some limits there, more so in the phase encode direction than in the frequency encode direction. All right. So what's highlighted here is the things that changed. So I'm not going to change everything every time. And in fact, in the lab on Wednesday, don't change a bunch of things, right? Be good scientists, change a parameter, see what happens. Change a parameter, see what happens. And the other rule of thumb on Wednesday is the scanner should always be running, right? You should just keep cranking out another test, another example. If you sit there and talk about it for 10 minutes before making a change, you won't win. And it's a little competition, right, between you and the other group on that scanner. So keep scanning. Okay, so the one obvious thing might be to decrease the field of view in both directions, and that's good because it helps our resolution, right, our field of view gets smaller, matrix stays the same, resolution gets higher. So that's good. And our relative signal to noise drops, but it drops quite a bit, but maybe it's okay because it's still above this kind of arbitrary criteria of 1, right? Unfortunately, we changed the field of view, we didn't change the matrix size, so our acquisition time didn't change. So we helped ourselves out in terms of resolution, but not really in terms of maybe overall image quality. So the artifact's still going to be breathing motion. The advantage is going to be, say, maybe acceptable or higher signal to noise than, say, 1.0, and you'll have a more focused field of view. So that sounds good. The disadvantage is that our scan time is still too long, and that means that there's breathing motion. But this is what the image might look like. So focusing on the image for a second, we chopped off the arms. That's what it looked like previously. We can do that. We tighten up the field of view. We lose the arms without having aliasing artifacts in the frequency input direction. When we tighten it up in the AP direction, we can tighten it up more, but we tighten it up some to begin with. And this is what happened to our K data, right? So before, the K data was sort of more bunched up in the middle, right? If it's more bunched up in the middle, the step sizes are smaller. If the step sizes are smaller, then the field of view is bigger, right? So you should keep making these connections between the K data that we sample and resolutions, field of view, scan times, all these things. So better resolution at least, but still we have this breathing motion, right? So we're not totally done there. So I think I'll leave it at that. Here we start seeing an example of adding partial phase field of view. That's a term we haven't quite used yet that just says we can change the field of view in the phase direction differently than the frequency encoding direction. The first two examples were square, but that's not a strict requirement. We can have rectangular fields of view. And so I think this is a good enough exercise, and it's pretty well spelled out. And you should be able to make these connections between the protocol, the K data, the image data. Go ahead and walk through these. I forget there's 3 or 4 more examples that get us to what looks like a good protocol, and then it gets to the other end of another sort of bad protocol. So you start seeing it as kind of an optimization problem. This is not, strictly speaking, an optimization problem, but it's the kinds of things that you should be thinking about for the lab on Wednesday. So I won't work through again all the different examples, but I think you'll be able to, and then we could always talk about it on Tuesday.